Okay, I think I'm recording. So this is my second attempt actually to make this video. The first one failed because I couldn't upload all the video clips because they were too long. So I'm going to make a bunch of really short clips. Okay, so first of all, we are learning about balancing chemical equations, and this is based on the concept of the conservation of matter. So that means that mass is never created or destroyed. This is something with which I believe you are already familiar from other science classes. We've even talked about it. Now, everything with mass is made of atoms. Therefore, the number of atoms before and after any change must always be the same. That's the basis for this lesson. Okay, here's our second clip. So when we're counting atoms, we need to be able to count them within chemical formulas. So if you look at H2O, for example, what it means is that there are two atoms of hydrogen and one atom of oxygen. A slightly more complicated formula is the formula for calcium phosphate. This is the phosphate ion, PO4, with a -3 charge. This is a calcium ion with a +2 charge. But we can just count the atoms without regard to what ions they're part of or what the charge is. So it says here that there are 3 calcium atoms. The PO4 is in parentheses with a 2 outside. That's a multiplier. So that means there's 2 phosphorus atoms. And remember, this is a multiplier, so 2 times 4 is 8. Don't make a mistake of doing 2 plus 4 is 6. There are supposed to be 8 oxygen atoms here. Okay, so I'm cutting clip short here. So the next thing I want to talk to you about is that when we do chemical equations, we need to take into account the fact that if we're going to show that the number of atoms is the same both before and after the change, then we need to be able to change the number of molecules involved in a chemical reaction. So a coefficient is what we'd use to do that. And a coefficient is a multiplier placed in front of a chemical formula. So like you can see here, if I put a 2 in front of the H2O formula, what it means is that although there's 2 hydrogens in the formula, I've got 2 of them total. So 2 molecules of water is one way you can represent what this means. So I've got 4 atoms of hydrogen and 2 atoms of oxygen. Okay, you can also represent this to mean 2 moles of water, but we'll get to that. 7 in front means I've got 14 atoms of hydrogen and 7 of oxygen. Okay, so it works exactly the same way. It's a multiplier. What if we had a multiplier in front of the calcium phosphate? So we've got 3 calciums in the formula, times 2 is 6. Similarly, we have 2 in the formula for phosphorus, times 2 is 4. 8 for oxygen, times 2 is 16. And that's how the coefficients work in front of chemical formulas. All right, so moving on. This is a chemical equation, and we're going to learn how to balance it. So balancing a chemical equation is done by putting coefficients in front of various formulas until the number of atoms on each side of the equation is equal for every element. So this equation shows what's called a decomposition reaction, where you have potassium chlorate, that's the name of this compound, decomposes to become potassium chloride and oxygen. We're going to learn how to write these words, these equations out in words, so it's good to sort of hear them in words to begin with. And what this would look like is if you had a test tube with this in it, it would be a white powder. You'd put this over a hot flame like a Bunsen burner, and it would melt and it would bubble. And the bubbles would be full of oxygen in this case because the compound is literally breaking down to these two different substances. So to balance the equation, first you start off with a blank equation or a skeleton equation. It sort of has some blank spaces in front of the formulas, and we make a chart to keep track of the number of atoms of each kind. So we've got 1 potassium, 1 chlorine, and 3 oxygens on this side, 1 each of the potassium and chlorine on the right, and only 2 oxygens on that. All right, so now that we've counted up the atoms on each side of the equation, we need to make them equal. We do that using something called the least common multiple, which you may remember doing in math class at some point. And it simply says that it's the smallest number that two numbers can multiply to become, whether by each other or by some other number. So we've got 2 and 3 for oxygen. Those are not balanced, but the other ones are. So we need to ignore the ones that are balanced and go for the one that isn't. And we've got 2 oxygens here. The least common multiple between 2 and 3 is 6. And so we need to put a 3 in front of the oxygen molecule on this side. That changes this to a 6. You should always update the little chart underneath. Now, to change this to a 6, you may be tempted to just change this to 6, or you may be tempted to stick something in here, but don't do that. Don't stick a coefficient in the middle of a formula because it just isn't symbolically meaningful. It isn't the way that we write things. So it doesn't make sense to do it. We had to put the coefficient in front of the whole thing. So that does change this to 6, which is what we wanted, but it does change these to 2. Okay, we have to, acknowledge what's happened here. Okay, with that coefficient, we've got 2 of each of those. So, but that's actually not that big a deal in this particular equation because we can just put a 2 in front of KCl on the right-hand side to make those become 2's. And now it's all balanced, which you can see because you've got the same number of each type of atom on both sides of this chemical equation. Okay, so the previous reaction was called a decomposition reaction, which I wrote in. This one is a combustion reaction. This is the same kind of reaction you get whenever you burn a compound containing carbon and hydrogen in the presence of oxygen, which there's lots of in our air. And so this is methane, but it could easily be any other compound of carbon and hydrogen, like, say, candle wax. Maybe this will look familiar from that lab long ago. So I went ahead and wrote out the equation and tallied up the number of atoms on each side so we could see how this looks. So carbon is already balanced, but hydrogen's not. So we're going to put a 2 in front of H2O, and that changes that to a 4. It's always a good idea to take into account one of the elements that appears in 2 molecules on the same side. Do that one last. Oxygen often in the combustion reactions is like that. Now, what I've done is not only changed the hydrogen to 4, but I've changed the oxygens as well. This 2 is the same. 2 plus 1 is 3, to total oxygens. But now I've got 2 plus 2, so I actually have 4. Okay, now the least common multiple between 2 and 4 for oxygen is 4. So I'm going to put a 2 in front here to give me a total of 4 oxygens, and that will balance that equation. All right, so let's do another equation. I realize I'm talking really fast here, but I'm trying to keep these clips short so that my limited bandwidth can handle uploading them. Okay, so this is a type of synthesis reaction where you have 2 reactants and 1 product. These can both be elements like they are here, or they could be compounds. Anyways, when you balance this equation, there's something that happens depending on which way you do it, which may make you feel a little uncomfortable. That is that you may need to make a change partway through. Let me show you what I mean. So iron is 1 and oxygen is 2 on this side. On this side, iron is 2 and oxygen is 3. Now, we happen to have written iron first, so let's balance iron first, which I think by now you'd guess you'd put a 2 right there. So we've got 2 iron atoms on the left. So we've got 2 iron atoms on the right. Fine. All right, and we've done this before, right? 2 and 3 for oxygen. We've got to find the least common multiple, which is 6. So we multiply this one by 3, and we multiply this one by 2. Good. Well, except there's a problem, right? When I multiply the whole thing by 2, because I have to, I can't stick the 2 in the middle, right? Again, don't stick anything in the middle of a formula or be tempted to change a subscript. Changing one of these changes what the compound is. Okay, so you can't do that. But since I had to put it in front, it does change both the iron and the oxygen. You may be reluctant to do that. Don't be, it's fine. I know it messes this side up, but that's what erasers are for, or God forbid, you could just cross it out. It's fine. Okay, so change it to a 4, and you're all set. Okay, so I'm going to do one more and risk this not being able to upload again. All right, so let me take a minute to sort of remind you how certain kinds of ions work in ionic compounds. For example, if you have aluminum nitrate, aluminum has a +3 charge as an ion. Nitrate is an ion with 1 nitrogen and 3 oxygens, but the whole molecule has a -1 charge. And so it's able to enter into compounds as a whole unit. Right, so that's how aluminum nitrate breaks down. Sodium hydroxide, similar sort of a situation. Sodium always makes a +1 ion, and the hydroxide ion is a molecule with an oxygen and a hydrogen and a -1 charge. So, okay, almost time to wrap things up entirely here. Let's take a look at one more chemical equation. This is called a double replacement reaction because the ions sort of take the place of each other. The sodium ends up with the nitrate ion, and the aluminum ends up with the hydroxide ion. They're sort of doing a little dance and exchanging partners. So we're going to actually count ions here rather than elements because it makes it easier to balance this equation. Otherwise, we've got oxygen in every molecule, and it gets really complicated. It's much simpler to just count the number of ions of each kind. Right? Sodium ion hydroxide ion, aluminum ion, and nitrate ion. And then we can just count them up on each side like that and balance it accordingly. So let's take a look. Sodium's already balanced, but hydroxide is not. So we're going to change the sodium, okay, to 3 so that we can balance the hydroxide, right? We should balance the hydroxide by putting a 3 in front of the whole formula. That changes the sodium to 3 as well, which that messes up the sodium balance, but that's okay because we can go over here and make more changes until everything works. Right? That makes 3 sodiums on this side. It also makes 3 nitrates on this side, right? Because there's NO3. That's a single entity. That's a single thing. So we've got 3 of those now. So we'll write in a 3 right there, and then we're all set. Right? And it ends up working out pretty straightforwardly and simply that way. All right, so we're going to wrap things up here. And what I want to say is that this is something that takes a little bit of practice to learn. So be patient with yourself. Feel free to pause this video and go back over it. I do talk kind of fast. And there are a bunch of resources available that I provided to you, including a copy of these notes. And later this week, I'm going to ask everyone to please sign up in groups of 4 to 5 for a 15 to 20-minute session, either on Wednesday afternoon or Thursday or Friday morning. There's a sign-up sheet on the Google Classroom page. Please sign up by putting your name in there. Feel free to get in touch with friends and sign up at the same time. We can all get together at the same time. And that idea there is that it's for you guys to ask me questions and get the help that you might need with the material. All right, and always please get in touch with email or whatever other way seems to make any sense. So thank you very much, and have a great week.